We're now ready for section 6.2, and you can see our topics today. Two topics. We'll start off with what are one-to-one functions, and then we will end our lesson today looking at some examples of how to work with inverse functions. So let's get started. So a one-to-one function is a special function that the easiest way to identify them, if you're looking at a set of ordered pairs or a mapping diagram, is that they can't have any repeats in the range. Now we know to be a function, there can't be any repeats in the domain. So if there are repeats in the x's, then it wouldn't be a function at all. But to be considered a one-to-one function, look out for repeats in the y coordinates. So I just went ahead and gave you an example of each. The red represents one-to-one because there's unique x's and y's all the way through. The blue is not one-to-one because the number 7 appears in the range twice. So it is a function, but it's not considered a one-to-one. And that could also be shown using a mapping diagram. So the red mapping diagram shows unique pairings for x and y. Every x has its own y, and that's what it means to be one-to-one. However, over here, arrows got erased. Over here, 12 and 14 are sharing the same y. It's -8. And so this is not considered to be one-to-one. I guess you could think of it as 2-to-1, but we're wanting to know if there's a one-to-one relationship. Unique pairings from the x's and to the y's. Okay, so that's how you will be able to distinguish looking at ordered pairs or mapping diagrams. Here's how you can tell looking at graphs. We perform something called the horizontal line test. And the horizontal line test will show us, for example, if I do a horizontal line on this left graph, I only touch one point. Every time I do a horizontal line, I touch one point. So I'm proving that this left graph does represent a one-to-one function. But the right graph is not, because a single horizontal line touches more than one point. So you may remember the vertical line test from Algebra 2. That tells us whether or not a graph is a function. Well, the horizontal line test will tell us if the function is one-to-one. All right, now we're switching gears to inverse functions. And inverse functions are really pretty simple in mapping diagram situations, or if you're given a set of ordered pairs. I'll do this example that's a little bit different here because the book uses ordered pairs that have names and birth dates, but generally what you're going to see are regular points that would be plotted. So let's just say, for example, that this is a function called f of x, and it's got these ordered pairs in it. I'll just make up some ordered pairs here. We did this in Algebra 2. All right, so there's the function called f of x. Well, the inverse of that, and it's denoted by this -1, looks like a -1 exponent. This reads as the inverse of f. To get the inverse, I literally just switch places with the xy coordinates. And I got it. And so the same thing is going to be done here. With this mapping diagram, you can think of student as the domain and birth year as the range. So if you want to just go ahead and put these as ordered pairs. That would be, you're basically switching places with these. So 2003 would go with Joe, and you just switch domain and range switches. 2001, Kim, and 2002, Noah. And it says to state the domain and range of the inverse. So the domain would be the years, and let's go lowest to highest. And the range would be the names. Joe, Kim, Noah. Famous basketball player from a few years ago, University of Florida and Chicago Bulls, I believe. All right, so here we have 26 to 32 even. You're going to be doing some things like this, where you're basically switching the XY coordinates to come up with the inverse. Okay, now we're going to be proving that two functions are inverses of each other by doing composites. And that's what you'll be doing in 34 to 42 even. So we did this in Algebra 2 as well. So hopefully this will refresh your memory. So I've got these two functions, f and g. If I do this composite, f of g of x, and I get x, and then I turn it around and I do the g of f of x composite, and I also get x, then I'm proving that these two functions, f and g, are inverses of each other. And then we'll talk about this final sentence at the end about the domain of f and g. So I've kind of got this started already. Notice how I took the g function in green. I'm doing the f of g of x, so the g becomes an input into the f. And we'll see what comes out. So distribute the 3 times 1/3 x, 3 times negative 4/3, and then bring down this plus 4. And so far, it's looking really good. For the f of g of x composite, I'm left with x, and that's a requirement. And now let's turn it around and do the g of f. So the f becomes the input into the g. All right, so 4 minus 4, of course, would be 0. And you have 1/3 times 3x, which also is x. Okay, and as far as the domain, it says give any values of x that need to be excluded from the domain of f and g. Well, since neither one of these are fractions that have a variable in the denominator, we don't have to worry about division by 0. Neither one of these contain radicals where we have to worry about the square root of negative numbers. So we don't have to worry about excluding any numbers from the domain. So there are no values that need to be excluded. So we're done. All right, let's try this one. Same thing. That was the previous problem. Okay, let's try this one. So let's do the, probably doesn't matter which one you start with. We'll do the f of g of x composite first. So g inputs into f. 2 minus x. Okay, so distribute the 2 times this numerator, 8x minus 6 over 2 minus x. And I forgot the plus 3. And down here, I'm just going to bring this all down. So we got some common denominator work to do. So let's just come down here. This top fraction, our common denominator, is going to be 2 minus x. So dividing 2 minus x into 2 minus x, that's 1. 1 times x minus 8x minus 6. This is like dividing 1 into 2 minus x, 2 minus x, and then you do 2 minus x times 3. So you divide the old denominator into the common denominator, and whatever that result is, we'll multiply times the numerator. And we'll do the same thing on the bottom. 2 minus x will be the common denominator. So this doesn't change, but this one, if we don't divide 1 into 2 minus x, I get 2 minus x, and then you just take that result. I'll keep doing that. 2 minus x then multiplies times 4. 8 minus 4x. Okay, now we can put these together, combine like terms in the numerators. 8x minus 3x is 5x. Negative 6 plus 6 is 0. 4x minus 4x is 0. Negative 3 plus 8 is 5. This is called a complex fraction, and when the denominators, the 2 denominators from each separate fraction are the same, then it's like they just cancel. So you can just wipe out the denominators. And what's left is 5x over 5, which is x. Okay, so when we did the f of g of x, we proved so far that they are inverses of each other. Now we have to do the g of f of x. So f gets input into g. All right, so let's see what we got here. So distribute the 4. All right, common denominator, which will be x plus 4. So 8x plus 12 isn't going to change, but 1 goes into x plus 4 times, and then you just multiply. So it's going to be 3x plus 12. Same thing down here, common denominator, x plus 4. So 1 goes into x plus 4 times, and then just multiply that times 2. And then this doesn't change. All right, so we got our common denominator. So combining like terms in the numerator. Remember, you're subtracting both of these. So 8x minus 3x is 5x. 12 minus 12 is 0. 2x minus 2x is 0. And 8 minus 3 is 5. And again, these separate denominators of a complex fraction will just cancel out. 5x over 5. So we have proven that these are inverses of each other. And now we do have a couple of restrictions for the f function. The x cannot be -4. And for the g function, x cannot be 2. So those are the two restrictions on our domain. One restriction each. All right. 44 to 48, you're going to use this same idea of switching xy coordinates to come up with the rest of the graph. It's an interesting thing that happens when you have a graph and then you graph the inverse. The two parts, the graph, the function and its inverse, always reflect over the line y equals x, which is shown here. So the way you come up with the inverse, the part that's missing, is just switch the xy coordinates for points that are on the other side of the line. So for example, I'm going to take -1, 0 and make it become 0, -1. And that's like the mirrored image of that point. And that's how I come up with the inverse. Here is 0, 1. So the mirrored image, the inverse point would be 1, 0. And so here is 1, 2 in red. So for blue, it would be 2, 1. And then I connect the dots and you can kind of see how the missing part is made. So just switch the ordered pairs on the side that you're given and you'll come up with the inverse part. So those are 5 problems where you'll be doing that kind of exercise. And then finally, to wrap up this assignment, you are told that each one of these are one-to-one functions, and you're supposed to find the inverse and check your answer. The directions say to graph on the same coordinate plane. I'm going to mark off the graphing part, so when you get to 49 through 60, I'll save you a little bit of time. You don't have to graph the inverse and the original function on the same coordinate axis, so you could just skip that part. Okay, so let me show you how to find the inverse. We know how to find the inverse if we're given a set of ordered pairs. That's pretty easy. We just switch places with the xy coordinates. Well, if we're given a function, we switch places with the x and y variables. Okay, so you can just treat f of x as though it were y always. So the process goes like this. You're going to switch places x and y. That's step 1. Then you're going to solve for y. And when you solve for y, you will have the inverse. Okay, so for number 1, I switch places with x and y. Then I solve for y. And when I get down to solve for y form, I'd like for you to do this. The original function was called f of x. So let's call this the inverse of f. Just use that little -1 notation. So to check your answer, we're going to do those two composites. I want to see if when I do f of -1x, do I get x? Okay, so let's see. And I'm going to input the inverse in place of x in the original function. And sure enough, I get x there. And then if I turn it around, and do it the other way, inputting the function in, I also get x. So that's what it means by checking your answer. Okay. For number 2, switch places with x and y. So x will be equal to y cubed plus 2, and then solve for y. So we'll subtract 2 first. And then we will do the cube root of both sides. Another way of saying raise both sides to the 1/3 power. And that gets it to y. And so instead of saying y, I'm going to say the inverse of f. So I'm calling that the inverse. And to check this, you might be easier to think of this as it's the same thing if you think of it as x minus 2 raised to the 1/3 power. That would be a little bit easier to work with. Do either one. All right, so let's check it. Let's do the composite, letting the inverse be input. So I'm going to get my bearings there for a second. All right, so here's the inverse. And I'm raising that to the 3rd power, plus 2. So these two basically wipe each other out, becomes x minus 2 to the 1st. And that equals x, so we're good there. And then just turn it around and let the function go in as an input into the inverse. Just doing that here. So you see how those 2 minus 2 becomes 0. And then x to the 3rd raised to the 1/3 equals x. Okay. All right. I got one more, and I didn't leave a whole lot of room here. And let me just, I'll see if I can squeeze it in. So switch places with x and y. And then solve for y. So I'm just going to multiply by y minus 3 on both sides. And I'll go ahead and distribute the x. I'll add 3x to both sides. And then I'm solving for y, so I'll divide by x on both sides. And that will get y by itself, and so I'm going to call that the inverse. And then you just go through that same process of verifying. So input the inverse into the function, and you should get x, and then input the function into the inverse, and you should also get x. So you've seen a couple of those already. All right, that should do it. Your assignment will be worked on in class Thursday. So there's no assignment due for Thursday. So just make sure you bring your notes back and be ready to do some practicing during Thursday's class. And if you have any questions, I'll keep my computer handy, and you're welcome to email me as you're working on these problems if you have any questions. See you soon.